Hello all, my name is Uday Krishna from CICC bearing roll number 05D0. Today, I am here to give a presentation from the subject Applied Physics on the topic of classification of magnetic materials. Now let us see here. This is the introductory side, classification of magnetic materials, and my intro. I am Uday Krishna. Now let us see the magnetic materials. Firstly, the materials are classified into two types based on their magnetic property. One is magnetic materials and the other is non-magnetic materials. Here, in the given picture, we can see the magnetic materials and non-magnetic materials. In magnetic materials, most of the items are made of iron, which is attracted to the magnet. And here are non-magnetic materials, which are made of other than iron, so they are not stick to the magnetic material. In this video, we will be seeing in detail about magnetic materials. The materials which are attracted to the magnet are called magnetic materials. In daily life, we see many iron nuts and bolts are attached to the magnets. So those are the examples of magnetic materials. Now let us see the types of magnetic materials. Magnetic materials are generally classified into three types based on their behavior of materials in the magnetizing field. They are diamagnetic materials, paramagnetic materials, and ferromagnetic materials. Again, ferromagnetic materials are classified into two types. They are antiferromagnetic materials and ferrimagnetic materials. Now let us see them in detail. The first classification is diamagnetic materials. The materials which acquire feeble magnetism in the opposite direction of applied magnetic field when placed in an external magnetic field are called diamagnetic materials. This means that diamagnetic materials will develop the magnetization in the opposite direction in the presence of applied magnetic field. The examples of diamagnetic materials are inert gases, metals like bismuth, copper, zinc, copper, gold, etc. Mercury, glass, water, marble, etc. Properties of diamagnetic materials. Due to the different orientations of an electronic orbit in an atom of the diamagnetic materials, the resultant magnetic moment is zero. These materials do not possess permanent dipoles. No spin alignment is present in these materials. Susceptibility is negative. We know that susceptibility is represented by the symbol Xi. Relative permeability is less than 1. We know that mu r is equal to 1 plus psi. As Xi is negative, mu r is less than 1. Diamagnetic materials are temperature independent. The materials which do not depend on temperature is diamagnetic materials. In presence of the external magnetic field, the magnetic lines of force are pushed out from the materials. Then the magnetic flux density inside the specimen is less than the flux density of free space, B in less than B out. We can see the magnetic lines of force inside a specimen is less than the magnetic lines of force outside the specimen from the picture. At very low temperatures, the superconductors are perfect diamagnet. Superconductors are the perfect examples of diamagnet. Now let us see the paramagnetic materials. The materials which acquire feeble magnetism in the direction of applied magnetic field when placed in an external magnetic field are called paramagnetic materials. Now let us see some examples of paramagnetic materials. Oxygen, platinum, sodium, potassium, alkali metals comes under paramagnetic materials. The properties of paramagnetic materials are when these materials are placed in a magnetic field, a net magnetization will be induced since the moments line up in the direction of the field and hence there is magnetic moment along a field direction. These materials possess permanent dipoles. Spin alignment is random in this direction. We can see the spin alignment in this picture. The value of susceptibility is small and positive. Relative permeability is greater than 1. As we know that mu r is equal to 1 plus xi, as xi is positive, mu r is greater than 1. These materials are temperature dependent and it is given by the relation xi is equal to c by t, where c is constant. In the presence of the magnetic field, the magnetic lines of force are passed from the material. Then the magnetic flux density inside the specimen is greater than the flux density of the free space. We can see here the magnetic lines of force inside a specimen is greater than the magnetic lines of force outside the specimen. Now let us see the ferromagnetic materials. The materials which acquire strongly magnetized in the same direction of applied magnetic field when placed in an external magnetic field are called ferromagnetic materials. Examples of ferromagnetic materials are iron, cobalt, and nickel, etc. Properties. Ferromagnetic materials possess permanent magnetic moment even in the absence of an external magnetic field. The induced magnetic moment produced during the application of the external magnetic field is very large and it increases the magnetic induction inside the specimen. All the spins are aligned in parallel and in same direction in the domain. We can see in this picture all the spin alignments are arranged in the same direction and are parallel in direction, parallelly arranged. Susceptibility is positive and high. Relative permeability is relatively greater than 1. Susceptibility depends upon temperature and it is given by the equation xi is equal to c by t minus theta. When the temperature is increased, a ferromagnetic material converts into paramagnetic material. This is a property of ferromagnetic material. When ferromagnetic material is heated up to a certain temperature, those materials are converted into paramagnetic materials. In the presence of the magnetic field, the magnetic lines of force are passed from the material, then the magnetic flux density inside the specimen is greater than the flux density of the free space. We can see here the magnetic lines of force inside a specimen is very much greater than the magnetic lines of force outside the specimen. These materials exhibit magnetization even when the magnetic field is removed, that is, they exhibit magnetic hysteresis. These materials consist of a number of small regions which are spontaneously magnetized called domains. I will show the picture of domains. We can see here the material is classified into small rooms in which the magnetization is in a fixed direction. These are called domains. Now let us discuss antiferromagnetic materials. In ferromagnetic materials, the spins are aligned anti-parallel to each other and having equal magnitude. So net magnetization is zero. This type of magnetization is known as antiferromagnetism. The examples of antiferromagnetic materials are iron oxide, manganese oxide, chromium oxide, and salts of transition elements, etc. Now let us see the properties. Spins are aligned anti-parallel in the domain. We can see here that every spin is aligned in anti-parallel to each other. Susceptibility is small and positive. The temperature at which the antiferromagnetic material converts into paramagnetic material is known as Neal's temperature. Susceptibility is inversely proportional to temperature. That is, Xi is inversely proportional to T. Ferromagnetic materials. In ferromagnetic materials, the spins are aligned anti-parallel to each other and having unequal magnitude, so the net magnetization is not zero. This type of magnetization is known as ferromagnetism. The difference between the anti-ferromagnetic materials and ferromagnetic materials is change in the magnitude of spin. Now let us see the examples of ferromagnetic materials. They are ZnFe2O4, nickel ferrite, ceramic materials. Ferrites are the best examples of ferromagnetic materials. Properties are spins are aligned anti-parallel in the domain as same as ferromagnetic materials, but the magnitude is not same. So the net magnetization moment is not equal to zero. Susceptibility is positive and high. The temperature at which the ferromagnetic material converts into paramagnetic material is known as Neal's temperature and it is given by the relation Xi is equal to C by T plus theta. Susceptibility is inversely proportional to temperature, that is, Xi is directly proportional to 1 by T. As I said, ferrites are the best examples of ferrimagnetic materials. These are the classification of magnetic materials. Thank you all for giving me this opportunity. I am going to post this PPT in the description. Thank you.